back to chemical kinetics. Today's the day when we start talking about exactly how a reaction happens at the atomic level. In a bimolecular reaction, a collision has to happen for a reaction to occur. So this reaction, I'm telling you, is bimolecular, and a collision has to happen between Cl and Cl in order for this reaction to happen. It's very possible that the lone chlorine atom collide with a different atom, such as in this bottom step, where we have the lone chlorine colliding with an oxygen. That bottom step is an ineffective collision. The orientation is not correct. If you're trying to end up with a Cl2 as the product of your reaction, you need a Cl to collide with another Cl in order to break off into a diatomic chlorine and NO being ejected from that system. So in a bimolecular reaction, two things are colliding. That's what the bi is for. It's telling you two things are colliding. More details about this reaction. So if we draw a plot of the energetics of what's happening in this thing, we start with a shelf that has our reactants on it. Chlorine and ClON on one shelf together. That's a sum of the energies of the reactants. Then a collision happens. What does the collision look like energetically? It's way up there. The collision creates a very high energy species, a high energy complex called an activated complex frequently, but we will refer to the top of that hill as the transition state. So when the exact instant when those molecules collide, we create a very temporary high energy state called an activated complex, a transition state. At that transition state, you are making new bonds and breaking old bonds, and so that's a really high energy thing to do. And then as your bond is made and broken and things start to separate, you lose energy, you release energy from that activated complex state, and you end up with Cl2 and NO in this specific example. We can find the delta H of this reaction if this is an enthalpy plot. We could also find the delta G if this is a Gibbs free energy plot. But let's say this is an enthalpy plot, where we can do the sum of enthalpies of the products minus the sum of enthalpies of the reactants. That change is our delta H of the reaction. In addition to delta H, another important energy thing to point out is what's called the activation energy, and that's indicated by EA on the graph. EA tells you how much energy does it take these reactants to climb up that hill to get to that high energy transition state. Activation energy, you are putting in a ton of energy to climb up that hill. Activation energies are different for different reactions. We will also sometimes talk about the activation energy of the reverse reaction. Is it possible that these things can gain enough energy to climb up that hill backwards? Sure. When we talk about a reaction being reversible, what's happening is some reactants are climbing the hill and ending up to products, and some products are climbing the hill in the reverse direction to end up at reactants. And we have defined previously that when the rate of the forward is equal to the rate of the reverse, that's when chemical equilibrium is established. So when you have the same rate of product forming reactant as you have reactant forming product, that's equilibrium. But anyway, we're on to kinetics now. We said a bimolecular reaction has to have a collision in order to produce products. There are two main reasons why you may not produce products, even when things collide. Number one reason is maybe the orientation is wrong. So if you go back to our first slide, the chlorine bumping into the oxygen, that was wrong orientation. More importantly than wrong orientation, they may not have enough, the molecules may not have enough energy to overcome the activation barrier. So if I look at a spread of the energy, spread of the kinetic energies of my molecules in a given system, given by this plot on the right, if I say E1 here is what my activation energy is. That's the amount of my activation energy barrier, the value of my activation energy barrier. Everything above that activation energy does have significant enough kinetic energy to overcome that activation barrier. Everything below that kinetic energy does not have enough energy to get over the activation barrier. So the activation energy of a reaction, the activation barrier, is really an important thing, and we will spend a whole day talking about the activation energy values, how to find them, how they change in different scenarios, but that's not today. Today, we're introducing you to mechanisms overall. So when two things or multiple things, when things collide in a single step, that's called an elementary step. So this step that we've seen again and again and again now is an elementary step. What's cool about elementary steps is that if you know the coefficient in your elementary step, that coefficient is the exponent in your rate law. So if this is my elementary step, it's one molecule of chlorine colliding with one molecule of ClNO. So I can know that my rate law for this reaction, this elementary step, is Cl to the first power times ClNO to the first power. This is a reaction that is first order in chlorine, first order in ClNO, second order overall. I know that because I know that what I'm given is an elementary step. So a reaction mechanism is simply a series of elementary steps, a sequence, a compilation of multiple elementary steps. So in this given reaction, it says 2NO and 1O2 get together to make 2NO2. Is it likely that three things collide all at once, especially three gases? Is it likely that three gases collide all at once to form 2NO2? No. This reaction is broken down into a series of elementary steps. There's one where two NO molecules get together to make something NO2. And here's another elementary step where that NO2 then combines with, into O2, then combines with O2 to give you your product, 2NO2. If I sum that stuff together, I get my overall reaction. But wait, what? Where did N2O2 come from? N2O2 is absolutely 100% detected when you turn NO and O2 loose together to do a reaction. You observe N2O2 in the process of that reaction. Something that is a product early and is consumed later is called a reaction intermediate. Reaction intermediates can always be canceled, and they never show up in the overall balanced equation. Let me say it again. Reaction intermediates are species that show up early in the equation, early in an elementary step, and are consumed in a later elementary step, and are never shown in the overall balanced equation because they always cancel out. So N2O2 is our reaction intermediate in that given equation. So I started off by saying a bimolecular reaction, a bimolecular reaction. Well, we will use these terms somewhat commonly. Unimolecular, bimolecular, termolecular. That means one thing in an elementary step, two things in an elementary step, three things in an elementary step. Bimolecular is, I would say, by far the most common. A bimolecular thing, two things colliding. Termolecular, three things colliding, not so easy. Unimolecular, one thing falling apart, generally, not as common as bimolecular. So when I have multiple elementary steps, it makes sense that some of them might be faster or slower than others. And how do you determine what's faster and slower? If I go back to my same given reaction and I draw an additional reaction, or draw a reaction coordinate diagram for these guys. Reaction coordinate diagram always shows a shelf that has reactants on it and a shelf that has products on it. Reactants on one shelf, products on another shelf. But I know the mechanism here, so that's why my reactants shelf is actually just the reactants of my first elementary step. My products shelf is the legit final products of my reaction, but in the middle, I have another shelf where I have the reactants of my second elementary step. So I've got reactants for the first elementary step on a shelf, reactants for the second elementary step on a shelf, and overall products on a shelf. Reaction coordinate diagram. Reaction coordinate diagrams also show lumps and bumps connecting all of those shelves together. And the size of those lumps and bumps and humps tells me some stuff about the reaction. This barrier, this first hump, is taller than this second hump. So what that actually tells me is this reactant, it's going to take a lot of time. It takes a ton of energy to climb up to this first transition state up here. But once you actually climb to that transition state, you slide down into this valley, into this trough, and hang out for not long, because it doesn't take much energy at all to climb that hill to then whee down to the other side. So what that really tells me is it takes a long time to climb this barrier, but it takes a lot less time to climb that barrier. So that second step is the fast step, while the first step is the slow one. I'm not saying anything about exactly how fast or exactly how slow so far, but comparatively, the first step is slower than the second one because the first hump is taller than the second one. That's good enough for now.